Let me welcome you all to our bi-weekly session of the Healthy Planet Action Coalition. This should prove to be a particularly stimulating session. As you know, the mission of HPAC is a bold enterprise. We advocate for humanity coming together to create and implement a comprehensive plan to avert climate disaster by blending the three pillars of the triad: direct cooling, emissions reduction, and greenhouse gas removals. But in order to reduce global heating back down to below 1 degree centigrade and thus restore a healthy climate, we're all very concerned with how these ambitious goals can be achieved. And that begs many important questions. For example, how can humanity do this blending of the three elements of the triad into a comprehensive plan? How long will it take for this to happen, considering the different potential trajectories for the reduction of emissions, greenhouse gas removals, and near-term deployment of sunlight reflection methods? So there is a great variation in the judgment of different scientists and policymakers as to how fast these things can occur or should occur, considering the technical, economic, and social constraints. There's also great variation in the judgment of how rapidly and seriously the deterioration of global weather systems will cause major human suffering and ecosystems degradation. And there's great variation in judgment of how soon the self-reinforcing feedbacks of Earth systems will be activated, and whether these tipping points will reach a point of no return in the near future. So coming up with plausible and reasonable scenarios that blend these elements together is complicated and has so far pretty much defied comprehensive analysis. But that is no longer the case. Bruce Parker, our fellow HPAC member, has been on the ball and thinking about this challenge for quite a while now. And he has produced a model that can enable us to create a wide range of scenarios to enable individuals to better understand the implications of these processes in the coming decades. Bruce, as you probably know, is a professional data systems analyst living in the Washington, D.C. area. He recognized that he has the analytical skills to tackle this challenge, and he's been hard at work to review the literature, isolate the important relationships, correspond with our colleagues like Mike McCracken to get scientific evaluation of some of the issues, and to embed them into a model that is intended not only for scientists, but for the public at large. So we're delighted that Bruce is with us today to discuss the model and how it works. He's prepared to share a slide deck that covers the territory and engage with us in a discussion of how we can use this model to get a better feel for the future. Bruce, just a question before you start. Would you prefer to entertain questions during your presentation, or would you like to wait until the end and when we open it up for Q&A?
Yeah, I think wait till the end. I'm sort of looking at when I do my slide deck, I can't see anything. All I see is my slide deck as I'm running through. So
okay.
I can't see pictures. I can't see hands coming up.
Oh yeah, right. That is a problem. Yeah.
Also, it's a very. I'm going to go through probably relatively quickly because it's complicated. You see some equations up there. Don't worry about them. Just trying to get a feel for how this thing works. And what sort of going through this, what we really need is another like a 2-hour session on scenarios. Understand? Okay. But we'll talk about it at the end and figure where we go from here.
Fantastic. Well, Bruce, the floor is yours.
Great.
Yeah.
Like the slide share, and let me see if I get this at screen. I think I want screen. Share the screen. And the slide deck.
There we go.
You got it?
Yep, it's
Okay,
yep, it's right
I can
there.
see that, and I've got enough going on there. Okay, well, thank you, Dennis, for your introduction and for helping me get started on this development of the Scenario Explorer. I'd also like to thank Mike McCracken, who's actually the only one I know who's taken a look at it. He's been very helpful in finding lots of typos and had been very helpful in some wording on this thing. Because I've sort of been, as you go through and develop something, I have had time to go back and look what I wrote. I sort of put things out there, so I've got to get started on this. So thank you both for, oops, I want to go back one, for getting me started on this. I started working on the Scenario Explorer after a chance meeting with Dennis in an HPAC Zoom meeting last October. He had come up with a emissions pathway for the HPAC strategy document and had what seemed like a very simple need. Are there simple computer tools that can be used to estimate the amount of solar radiation management that we need to limit the temperature increase to 1.5 degrees for this emission scenario? Now, straightforward, right? This is 2024, the RI 25, lots of stuff going on. But no, I sort of figured what happened is everybody's stovepipe. There's nobody who's responsible for this. Everybody goes his own way, and no one set up a whole, a general way of dealing with this. So after providing some little background information, I'll lead you through the model's calculations and then briefly things on projection scenarios and pathways. Then see what the model works with. Next will be an online demonstration of the Scenario Explorer webpage, followed by discussing one important way the Scenario Explorer can be used, and that's to conduct what-if analysis. And finally, I'll be asking for help for ways that we can improve the site to further HPAC's mission. So I've been developing web-based database applications for over 20 years. I've been analyzing climate data for at least as long. So developing a simple model that could be used as Dennis requested seemed like a great challenge. The temperature increase in a particular year is primarily based on total radiative forcing. So in order to work, the model needs to know the relative radiative forcing of the greenhouse gases other than CO2, because all the emissions pathway has is CO2. So I looked at the current radiative forcing values to gain some insights. This is a standard diagram of the major radiative forcing elements. Note that CO2, CH4, and NTO make up, these things here make up almost 90% of the greenhouse gas emissions, of which there are dozens. The data for the scenarios that I used to create the formulas for the model generally did not include many of the forcing elements shown in the diagram. I've circled those, but did include the values for the total radiative forcing. And to help simplify the model's calculations, I subtracted the total radiative forcings of CO2, NTO, CH4, NTO, and aerosols from the total forcing to get a value for something I call other radiative forcing, and use those 5 forcing elements in the calculations. I next analyzed the data from existing climate models to see if there was a way to develop a series of formulas that could be used to get from CO2 emissions only to a reasonably accurate temperature increase. I think I've come up with some really relatively good correlations. I then developed a temperature calculation model with 3 major steps, which I'll cover in a few slides. I'm still looking for someone to validate my approach, but the model seems to be useful as it's based on data from well-known climate models. In the meantime, please feel free to experiment with the web page's function, but don't assume that the results are 100% accurate. And again, this is what I've developed is simply not even a simulator. I don't have anything to do with models and emissions and stuff like that. I simply use formulas to come up with an expectation for the temperature increase. As I mentioned before, the model uses values of these 6 forcing elements to calculate the expected temperature increase. The radiative forcing of CO2 cannot be calculated directly from CO2 emissions. And for a CO2 emissions pathway, such as Dennis likes to use, it does not include these other forcing elements. So you have to ask them a way of inferring values for these for the calculations. I'll now quickly describe the calculations, as this will help you use the Scenario Explorer. There are 4 primary sources and sinks of CO2. for a simple pathway, we can assume there are not any removals, but just we start off with CO2 emissions. We do have to take feedbacks into account. And what I do here is the feedback the IPCC uses is based on the temperature in 2100. So what I made for this model is I take a look at the expected temperature in 2100 and say, what sort of feedback should I expect? What's the temperature going to be? And then I can calculate a value for feedbacks. Now that we have values for the feedback emissions, I can compute the total net CO2 emissions for each time period simply by summing these sources and removals. And note that this scenario program, I don't go year by year, I do in 5-year intervals, because I wanted to allow people to input values for the various years, and someone does not feel like inputting values for 75 years. That would have been way too much. But you can easily do it for 25 or so. And given that total CO2, I now can get I can now compute also get the cumulative emissions also. The next step is to estimate how much the atmospheric quantity of CO2 will change based on net CO2 emissions. Currently, about 45% of CO2 emissions remain in the atmosphere. This is often referred to as airborne fraction, but the percent will be much less when the CO2 emissions are reduced significantly. And this graph shows you, this graph is based on data from the En-ROAD simulator, and I used it to chart if I give for a certain set of CO2 emissions, how much ends up in the atmosphere. And you can see this is that once you get under 20 or so gigatons of CO2 emitted per year, you end up losing CO2 from the atmosphere due to the land and ocean sinks. The other thing I like to do, for most of the formulas I derive, I like to create a graph that shows how well the formula works. In this case, I took 8 En-ROAD scenarios of various temperature increases from 1.6 to 3.0 degrees over in 2100 and calculated the CO2 concentrations from 2025 to 2100 and compared them to the CO2 concentrations for each scenario. So here you've got, I go start off at 2025, work my way up and say, okay, based on the emissions on the En-ROAD scenario and their ppm that they calculated, this is how my model compared to the calculations for each of those scenarios. For 3 degrees, it doesn't work at all, but we're not so much worried about that. But for the rest of the scenarios, I'm within 5 parts per million in 2100 of what En-ROAD came up with. So to me, that's pretty good. So once you get the change in, now we know the expected rate of change in atmospheric concentration of CO2. I add that to my previous year's value and I come up with my current year's value. The next step then, and given the CO2 concentration, we now need to figure out the value for the CO2 radiative forcing, and I had a formula developed from the IPCC data. And so basically, again, here's a formula for it. Here shows that based on the amount of radiative forcing, based on the ppm for a given year, here's the amount of radiative forcing to expect from CO2. And again, this graph shows it calculates, that's 6.123. I'm looking to see how well did my model work. And what I did was I said, okay, let's take what my model expects the CO2, the radiative forcing to be versus what was it in the model, what was in the scenario. And these are 14,000 calculations that done in the models. I'm generally within 1% of the original value. So again, that should be, that means I'm pretty close. Yeah, next we need the radiative forcing values for the other 5 major radiative forcing elements. We've got CO2, but now I need them for the other. And some emission pathways scenarios include those values. But again, if you start off with a CO2 only pathway, you don't have it. So I need some way of inferring what a good value for the radiative forcing is going to be. And I did that. Well, I think it's relatively straightforward. So if a non-CO2, if I don't have this non-CO2 radiative forcing values, I need to calculate them. I first calculate how close the CO2 pathway comes to these two baseline, these two SSP scenarios. Oops. And you can see over here what those the radiative force of those scenarios are. So I wonder how close to one of these, and these are sort of like a minimum and maximum values of the various SSP scenarios. I try to look at how close is it going to be here, and the closeness is then used to determine the various non-radiative forcing pathways for the scenario. So here we go. So, for instance, if I say I have a scenario, a emissions pathway, my total radiative forcing in 1200 was the way that keep forgetting the mouse does some such. Was 5.7. That's halfway between these two values over here. Then what I do is take a look at the CH4 pathway for methane for a CO2 only pathway, and these are the two values for those two scenarios, only halfway in between. So based on that, I say, okay, we're probably going to be about 6.6 watts per square meter per year for the scenario, if that's the value. So I do that for all the different non-CO2 path radiative forcing amounts, and that way I come up with an estimate or a reasonable value for what it might be. And this is a default value which the user can adjust if you think it's wrong or you'd like to see something a little bit different. Now that we have a value for the total radiative forcing, we can calculate the value for what I refer to as a climate factor. The term climate factor is something which I've originated. It's simply the ratio of the temperature increase to the total radiative forcing for a specific year. And because it was derived from IPCC data for a 67% chance of not seeing a temperature increase in 2100, it incorporates the climate sensitivity that was used by the various climate models. It's also interesting to note that it results in temperature increasing by 0.26 degrees centigrade per decade for the next few decades. If the scenario that I'm using, for instance, AR scenarios, includes the temperature increase values, I calculate the climate factor from the scenario's data. But the pathway does not include a temperature. Again, I have to come up with a way of calculating it. And so what I do is I use it based on a formula based on the climate factors from the IPCC. So this shows the climate, what I call a climate factor for 8 different climate scenarios, 8 different SSP scenarios, which starts off down around 4.9. And what I want to know, and if I plot a polynomial based on the ppm and the scenarios value of climate factor, I come up with a graph like this. I get this polynomial, and I simply say, okay, if the ppm for the CO2 only scenario was in a particular range, I can say what its climate factor should be. And once I get the climate factor, it's simply the temperature increases, the climate factor times the total radiative forcing. Very simple, very straightforward. Not 100% accurate, but hey, you've got to do something. This is a graph which I'm not going to talk about much, but I thought would be very interesting. It shows the relationship between temperature change and radiative forcing for a variety of CO2 concentrations. And for instance, if I'm at 450 parts per million, and I'm on I'm right up here on in 2045. So in 2045 at 450 parts per million, that will 1 watt of CO2, 1 watt of CO2 of albedo change will drop the temperature half a degree. So this gives you some idea. Just want to get an idea of how much solar radiation management do I need to affect the temperature. These little graphs might be able to help you out. I thought some additional background might be useful before starting the demo. Climate scientists use complex computer models to forecast possible future temperature increases based on assumptions about government climate policies, population growth, GDP, energy prices, and so forth. So the temperature increases due primarily to change radiative forcing, The output of all model runs usually include emission pathways to the various greenhouse emissions and aerosols. So Scenario Explorer used to allow users both to explore those emissions pathways and to develop initial ones. Projections. Okay, a projection is simply based on current emission and expected government policies and commitments. For example, the not negative national defined contributions. They often offer variations, some components like energy prices and such, and they generally only short term, like through 2050. So this slide shows the projections for made by MIT and IEA, the ones I could find, and this is the CO2 pathway for HPAC's pathway. And note that, first of all, note that for IEA and MIT, they kind of started off back in the low 30s. So they're just probably using CO2 energy emissions rather than total CO2 emissions. But note for IEA and MIT, for your standard ones, the temperature, the CO2 emissions don't change much in the next 25 years. So again, as one develops scenarios and talks to you about what sort of emissions should we expect in the next 25 years, we really should not expect them to go down much. And you'll see that's the case with many of the other scenarios. And also the announced pledges by EA begins something which says a little higher emissions, and the HPAC one tracks that pretty closely. So there's a good chance that the thing that Dennis came up with is actually optimistic. Scenarios are useful for determining what needs to be done to accomplish a particular goal. They're often not realistic in what is politically possible, like, for instance, getting to net zero in 2050. Oops, actually, I get this. I get that off of there. Forgot about that. Sorry about that. Examples of scenarios you're probably familiar with: the RCP's representative concentration pathways from the earlier IPCC reports. And what the IPCC now uses is what's called a shared socioeconomic pathway. And these are climate change scenarios that project how the global society, economics, and demographics could be changed by 2100. And they're used to analyze how these changes could affect both the climate and greenhouse gas emissions. I'm not going to go into this image in detail, but indicate some of the factors that go into developing the SSP scenarios. And you can see from it the breadth of what items are analyzed. Note that within the AR6 data, I have data for 50 different SSP scenarios. The numbers are like 1 through 5, whatever. But we don't have time to discuss this today, but there's an About Scenarios menu option on the webpage. And eventually that will cover more of this information so people get an idea more about what these things are like. But what I would like to cover next, and to give you some insight, is on some of the SSP scenarios. And for instance, this graph shows the net anthropogenic emissions from now until 2100, and they run the gamut from below zero in 1880 to well over 100 in 2100. But if you look at the carbon removal, you show how heavily these SSP scenarios rely on removing carbon removal techniques, and we know for a lot of people they're not sure these are going to work as needed. And then finally, what you can see here is for most of this, even though these SSP scenarios, the majority of them have emissions stay constant. The gross CO2 emissions are not changing much in the next 25 years, or even go up. And they simply bring them down by carbon dioxide removal. I just thought that'd be something interesting to point out about people's reliance on those. Pathways, okay, all projections and scenarios have greenhouse gas emissions pathways, but a pathway could simply be one for CO2 emissions as one for HPAC. The temperature increase can only be forecast by estimated emissions of other greenhouse gas emissions, as we talked about earlier. Oops. Once a temperature increase model is completed, it can be incorporated into the Systems Explorer webpage. And used to satisfy Dennis's need of being able to estimate the solar radiation requirements. The website contains too many options to cover today, but I'd like to mention 2 of them before I start the demo. One is there's an about scenarios things to provide information about scenario projections. Another one is on consequences of exceeding 1.5 temperature increase. So this would be a great place to have more information for people to understand how the implications of what we're gonna do. Okay, so next, time for online demo. And I need to escape, go here, oops, there, okay. So this is the home page. I'm gonna make this a little bit bigger. Control plus. As you can see, it's just relatively straightforward. As my friends know, I can create websites, but I'm lousy at making them graphically interesting. Since you're most likely interested in how the model gets used, I'll start with the Temperature Explorer. Smaller here. There we go. The Temperature Explorer defaults to showing data for what I refer to as a moderate scenario. Oops, left it off. Sorry about that. Left it off. Did not reset this back. Oops. Oh, I have one extra one on here. Okay. This is what I refer to as the moderate scenario. So basically the HPAC planning scenario. There are a couple of places where you can get instruction. There's a little tab here and a place where you can click. So when you first come to the website, I recommend you go and you take a look at the different instructions just to get an idea of how this thing actually works. But this Temperature Explorer defaults to having a temperature increase of 1.5 degrees, and I'll get more of that in a minute, but this shows the carbon dioxide removal and the SRM requirement. I want to hit 1.5 degrees. I wanted to compare this to another scenario, for instance, SS 3.5 scenario, 534 scenario. I'll just click up here, and that scenario then pops up. Note that this thing has a underline, the little dashes. When you see dashes, you can just hover a mouse over that, and a tooltip will pop up. And sometimes you can actually click on it to get additional information. Oops, I can get that rid of there. So anyway, what I'm trying to do is enable many ways for you to help understand how the model works and get information as you're going through it. If you want to compare this to the different scenarios, those two scenarios, mouse down, yeah, that's mouse goes down, okay. Go plus. There are probably 30 graphs like associated with these different scenarios you can look at, and here are a couple more, and you can use this to say here are two scenarios. Their anthropogenic emissions seem to be pretty close in line, but again, the difference between the two is one relies a lot on emissions removal, and the other one does not. So let's give you a flavor for how you can compare and contrast different scenarios. The other thing that as I mentioned, the scenario this defaults to an increase of 1.5 degrees. If you want to come back and say, well, gee, how do these requirements change? I'm going to back up on top. If you want to say, well, how much will my SRM requirement, my carbon dioxide removal requirement for a different temperature increase, you can just click on this little slider. So I get this down to 1.1. There you go, down to 1 degree. And you can see that I now need, well, the axis changed. You will try to tell, but you now have it, you now can see I need more CO2 removal to make that temperature increase. I wanted to go up here, I can say, oops, I get above 2.4, I don't need any. Down here, I need more. So you can just play around with that, say, so for a given scenario, how much additional do I need to make that temperature increase? Okay, now let's look at the other one, which I call the Scenario Explorer. And this enables you to look at individual scenarios. Ooh. Let me try to, I don't know why those scenarios aren't clearer than that. There we go. They're clear here. Okay. So again, this defaults to the, well, we were on the moderate on the SSP5, so let's go back to the moderate scenario here. There we go. There's too much to explore in a short demo, So I want to look at a few capabilities. Since a lot of this HPAC is interested in solar radiation management, there's an SRM button here you can click, and now you come to a form where you can input values either for SRM or for temperature increase. So let's say I want to go to 1.5 degrees in 2100. That shows you how how they go up, how it changes. And since you want to explore a little bit, you might go to you're not going to ramp up that quickly. You've got to change earlier. So back in 2060, I'm going to make this 1.9. You got a part way there. And there's a little problem with my algorithm right now. There are bugs in here. I need to work on getting this smoothed out a little bit. But again, this shows you that if you wanted 1.5 degrees in 2050 for this moderate scenario, I've got to be at 35 gigatons of CO2 emissions per year, negative emissions by 2055 or 2060, and leave it and probably stay at that range for a while. So this gives you an idea of how much you need to do that. And I also, since you're interested in these, I also developed a scenario which preloaded all that. I can go here to my 1.5 CDR, and this shows now I've got to change the model. This all should be negative, but this shows the requirements to reach 1.5 degrees in 2050. And if you then also want to look at what for solar radiation management, I go here and I click on that radio button, and this shows solar SRM requirements hit 1.5 degrees in 2050. I've got a scenario list. This lists all the different scenarios that are available right now. And I include this also so you can sort of get an idea of if you're looking for a scenario with a temperature increase or emissions reduction. But note that for 2050, most of the temperature increases are well over 1.9 degrees. So again, if people say, "Gee, we've got to reduce the temperature before keep it under 2 degrees in 2050," hardly any of these scenarios are going to work. Okay, what we go. I think that's pretty much. Other thing I wanted to show you, it's just quickly. I'm very concerned. I'm not getting into all today about costs, and I've got options here so you can pick up what the costs ought to be for things like seal rise and seal carbon dioxide removal. And I also provide this page here, which is a summary of how the model works. So we talked about all the 4 different emissions things, the different rate of forcing elements, and this goes you step by step for all the years what those different values are. So you can use this to compare and contrast values over time. And if somebody says, "Gee, here's a scenario that I think is important," you can say, "Well, did you include all these different variables?" I think that is the that's what I want. That gives you a quick tour. We have time after we can go back and do more of it. Now let's go back to the slideshow and continue from current slide. Okay. Oh, and the screenshots from this demo are included in the PowerPoint slides, so you don't have to have the program to actually look at them. To me, one of the most important things you can do, interesting things you can do with the Systems Explorer is do what-if analysis. So while global circulation models have done a relatively good job of predicting the past temperature changes, the climate system is beginning to behave in unpredictable ways. These models likely underestimate future yearly temperature increases. So, for example, Hansen thinks the rate of temperature is going to get a temperature acceleration in 2023, and Hansen expects a temperature increase to be 0.36 degrees per decade. Oh, I didn't show you that. I'm able to do that. One thing I forgot. But anyway, so it's a way you can use the scenario to do some what-if analysis. And this is just an example of something which I did. The numbers are probably a little bit off. I made some changes. But you can say if I use direct air capture, so I start with my moderate pathway, and I use direct air capture to reach 1.5 degrees in 2100. these are the values, these are the new values, and this shows how things have changed. And my temperature will increase a lot less, but it's going to cost a whole lot more. Again, really going into details, it gets the sort of thing that the scenario is good for. And particularly comes in handy because we know the energy imbalance is now growing, so that's going to contribute to the increased temperature. And again, this is from the climate reanalyzer. This is sea surface temperature a couple of days ago. This is insane. This is a non-El Nino year, and this temperature in sea level increase is way off the records. Anyway, we also know from Hansen that we had the albedo has been reduced recently, and this shows the change here. So the model can also be used to say what happens if the albedo changes over time. Let's go quickly. How you can help. I'm not going to go into the details here. Worry about accuracy, how you make it more usable, kind of scenarios, help with a cost section. Just primarily to say, maybe we perhaps form some sort of committee that can take a look at how do we take this stuff, this website developed, and make it and use it to further go after HPAC's mission. With that, and that's faster than I thought. And the share. Okay. Quick tour. Any questions? Any thoughts?
Yeah. I think we put our hands together for this piece of work, Bruce. Incredible job that you've done in providing this framework. And I think we should go back at some point and look at that list of things about how we can help, because that's the next step. But let's open it up. First hand I see on the screen is Sev Clark, and then we'll carry on around the table.
Bruce, can your model show what is the radiative forcing and change in, say, 2050 temperature if we were to increase global albedo by 4%?
That's a recommendation that, or showing it that way, Mike would crack it. Let me go back to, let me share again here. So let's go back to my model here, if I can remember where I did it. So you wanted to, let's go back to my moderate scenario, and you wanted to know so here's the, this is the moderate scenario. What was your question? What do you want to do?
I would increase the global albedo by 4%, say start it in 2040, and what will be the temperature in 2050?
Okay, this is watts per meter squared, so I need to change. I could make that whatever. So if I do half a watt per meter squared, whatever that means. This shows how the temperature increase changes. And if you look at the radiative forcing values here, you could probably show this shows the temperature increase. I don't show the radiative forcing down here, but yeah, it does. If we know what that is in terms of watts per square meter radiative forcing, then it does show that.
Well, what's can we work it out? What's the watts per meter at the moment, and what's 4% of that?
That's a watts per meter squared is now about what of the
albedo is currently 98 watts per square meter. It used to be 100, and so a 4% increase of albedo would be an increase of 4 watts per square meter.
All right, can you put that in, Bruce?
I don't think they ever get that high, but it goes down to, there goes 4. And that'll bring the temperature down to below what it is right now.
Well, that's what I surmise my buoyant flakes should be able to do by around 2040 if we start doing them pretty soon.
Okay, so that
basically it changes the albedo of the dark blue ocean from 6% to 12%, okay. And that I estimate is about the same as changing the whole globe albedo by 4%.
And you drop the temperature down below what it is today.
Yeah.
Below it was pre-industrial.
Below what, pre-industrial?
Yeah, I'm not. Again. Well, I mean, let me make first a comment. I'm not sure that my model does that particularly good job right now of things getting that well below pre-industrial, well below like 300 parts per million. That gets very interesting because you've got, although I don't know, this is the sort of thing that would be great to work with you to say, okay, what are reasonable numbers? And I can go back and look at my model and say, and then fix the model and make it work better.
Right.
So Bruce, your flux changes are all based on flux changes at the tropopause, right? Or top of the atmosphere.
Yeah.
So you have to be careful if you're going to talk about flux changes at the surface compared to what happens up above, but okay.
Again, and that's be very helpful to figure out, to understand how that works and what the difference would be, yes. Very interesting point, yeah. And again, yeah, this is the sort of thing where I took a stab at this. I'm not a climate scientist, so lots of little things like that which I need to understand and take into account. But once you take them into account, then I get the numbers right.
Okay. Greg, I think you were next.
Thanks, Bruce. This is fantastic as far as I'm concerned. It's great. I mean, it can always be made more sophisticated, but I'm very impressed. You've done so much work since I looked at it months ago, and it's great. So thank you. A couple things. One is most of the things you were looking at, you had both CDR and SRM being done.
Right.
I'm really pessimistic about CDR. Whenever you do one where you try to do everything with SRM and result and see how that goes. I mean, maybe you don't have time here, but I can try it myself. But I'm just very pessimistic at ramp up of CDR, depending on the method. That's just my sense of it. Another thing is, it would be good for me if you could make the SAI version of SRM in tons of SO2, because that's the kind of scale of an operation you're going to be faced with. And I think in general, having the ability to show what that means in terms of the scale of any sort of operation, and Sev just said, I want to reduce albedo by 4%. How many boats in the, I mean, turn it into, what is that going to require infrastructure wise to do? So that would, obviously it's another layer on top of it, but I think it's very important to say, this is what you're going to have to do. You're going to have to put, 100 million tons into the atmosphere for the next whatever it is, to do these things. Because that's the bottom line. And then the only other thing I was going to say is,
one thing on that. Great. Give me a number. Give me a formula that says for each tenth.
Well, okay, yeah, I'd have to. I mean, the common thing right now is it's about. I think it's about 100 million tons. Is that right? 100 million tons of SO2 in particular. One particular, the commonly used aerosol, to lower per year to lower the temperature by, I think, is either half a degree or a degree. I'm using, but anyway.
Well, I don't think it's that much.
No,
let's see. It's a million. It's a million ton. I was off. I think I was off by 2 orders of magnitude.
Yeah.
But
give me a number, we have calculated. I can add a line on there for you.
Yeah. Well, I think that. Yeah, I understand you can't do it. I mean, you have to get the input from people for each method they're talking about, and you also have to have these things like the difference between the what's happening in the lower troposphere or the stratosphere. But given that data, providing that layer or that ability to show how big of a project it is to deploy would be very crucial, I think. So that was so thanks for that. Yeah, I'll come up with something for SAI and vet it with, others, but that's one thing that would be great. The only other thing I was going to,
well, can I quickly mention here about CDR and costs? The thing is,
yes,
the cost model on that. So this is CDR for 1.5 degrees, and you're coming up with a carbon removal cost up in the trillions of dollars a year.
Yeah, well, that's what I'm talking about. It's insane. And not only that, I mean, it's just deploying all that infrastructure, which doesn't even, I mean, it just seems, I mean, you need a fantasy factor here, and they all have fantasy factors, but anyway.
This is why we need somewhere, we need in here. I'm not sure where we go in, maybe we do some of the consequences, but some talk about, what it really takes, how fanciful are those options?
Now, I mean, how can you actually do these kind of numbers? But that would be some more work and everything. But it would be extremely valuable to help people realize what realistic options are and what are total fantasy. Let me just ask the last thing, which is you in your comparisons, the comparisons you made during your slide presentation to test your own model, or not model really, but as you say, but calculations. I wasn't sure whether you were truly independent from the data you were using to develop your equations. I couldn't follow it closely enough. But
which one? Which one?
Well, maybe that one, for example, the one with the you just scrolled through it. There, the one with the diverging. There, this one, just for the hell of it. But difference between scenario RP and calculated, that is truly an independent check, or are they truly independent?
What I did was I used a formula to come up with these curves. I used En-ROADS data to come up with the curves. Then I said, okay, now that I've got an equation, how closely does it fit the data? It's so as long as if you could assume that the En-ROADS values are correct, that when they say here's the CO2 that goes up in the atmosphere, here's what CO2 here's the change, then it's matching this. It matches what En-ROADS does. Now, if En-ROADS is wrong, this will be wrong. But if En-ROADS is right, this should be a good scenario. It should be a good value. Because I took a year and I said, what are the emissions that year in these 5-year increments? And if these are the emissions, how much goes up in the atmosphere? How much gets added to the ppm? And I did that for all from 2025 to 2100, and say how does it compare with what the En-ROADS thought it should be?
Okay. I mean, I probably have to read some more and try
to talk about offline.
Yeah. Great. Thank you.
Later.
Yeah.
Okay. Let's move on to Jonathan.
Hey there. Yes, this is fantastic. Bruce did write my question into the chat as well, but basically, can you envision a checkbox or a spreadsheet row that takes into account the fact that over the years and decades, the natural carbon sinks will vary and they'll be able to absorb less as there becomes a higher concentration of carbon inside the sinks. And therefore, we can make the argument to people that we have to protect the carbon sinks during this whole process, or they will become a barrier to us. If they go down by, say, 25% over the next 10 years, and then another 25% over the next 10 years, then all these calculations would change because the carbon sinks are not pulling the carbon out that's being emitted.
Yeah, I could do that similar to this. I didn't show you this. This is the, let's reset the scenario. This is the, which one am I on? Modern. No, let's go back to modern scenario. Similar to this. It says there was a albedo change in 2023 of a certain amount. That raised the temperature. James Hansen thought the temperature increase would be 30.36 degrees per decade. That's to this. You could simply add another one was, what's the change in the, if it had the data, you could say how much less effective or is the ocean sink, how effective or how ineffective the ocean sink or the land sink, and you can do the same slider here and have a change.
Fantastic.
Yeah, yeah. Okay.
And again, looking for ideas and looking for data. I mean, I can't for something like that, I cannot. This is just a calculator. I'd have to have some way of saying, okay, well, what the sink is, or how the sink changes, and maybe just some way or another. I have to go with a formula. This is how to do it, but it should be doable.
Yeah.
There are groups that are protect the carbon sinks, you know, the great forests and the kelp forests and other carbon sinks. So having a slider, even without having the data yet, in place would allow us to show how critical it is to maintain those carbon sinks.
Yeah. Okay.
Yeah, again, we had a chat about it. Says how you incorporate it. Okay.
Well, you have a factor there on the ratio of emissions in the atmosphere to what is being removed. That's that 0.45 that you mentioned earlier, and that's a way of manipulating the perceived value of the sinks. So,
yeah, that's airborne fraction. But where I really get it is this temperature to RF ratio. What that you simply would mark this up a little bit. So there's more of a change when the temperature changes, and that would have the same effect.
Yeah.
But I need to work with someone who says, how much is the change going to be, so I can incorporate it into it.
Can you change the airborne fraction as a U? No.
This is calculated.
Yeah. Okay.
This what I might be able to do though. I could have the ability to change this ratio. Right now it's calculated, but I could make the ability to change that, so you could simulate that change.
I think that's what John was referring to. Is if you don't take care of these things, what happens? So
Again, this is part of the planning of how do we get a committee together and talk about these sort of things, and and again, you just can't put in. You've got to be able to explain it so it makes sense to people. And the people can't say, well, you got it all wrong.
Sure.
Excellent. Let's move on to Robert and then Ron. Robert?
Okay. Bruce, thanks very much. Look, my feeling is that what you've done presents a superb starting point for discussion. But I would like to question the assumption about the ratio between emissions and feedbacks. So you, if I recall correctly, suggested an emission figure of 30 gigatons per year and a feedback figure equivalent of 9 gigatons per year on one of your earlier slides. Now, James Hansen, in his 2024 article, commented that the darkening of the planet over the last decade had caused warming equivalent to 110 parts per million of additional CO2 emissions. So if you think about that, so a decade of essentially feedbacks from clouds, snow, ice, and aerosols that causing the loss of planetary albedo, if that's equivalent to 4 years of emissions, then that is more like 40 years of emissions. Then it will that suggests that ratio that you've got is questionable, and it opens the problem of defining what are feedbacks, what are forcings, what are feedbacks. And I know that this is something that Hansen has discussed at some length in his latest paper, which I haven't managed to fully read and understand. But I just wanted to open that up for your comment.
Yeah, two things there. One is these feedbacks are really primarily emissions feedbacks. And the way the IPC, if you look at the IPCC data, the IPC has assumed 0.166 watts per square meter of additional radiative forcing per degree centigrade, a long number. Anyway, what it boils down to is what are the feedback emissions in 2100 per degree centigrade? I'm set right now on 5. I could go down to 2. I could go up to 10. Those all change the emissions from feedbacks. Again, this is sort of, the model has it to say, if you don't like the way the feedbacks are being calculated, you can change it in the model. So the model allows for that.
So this is carbon feedbacks rather than radiative forcing feedbacks.
Yeah. Here's a radiative forcing feedback in the albedo increase per decade. Or should that be decrease? That should be decrease.
Yeah, I had actually suggested, I think, Bruce, that you actually make sure it says carbon feedbacks rather than climate feedbacks.
Very good. Yes, should be carbon feedbacks. Although by putting the units there, I've got it. Let's call it carbon.
They're sort of carbon. They're carbon cycle feedbacks. Yeah.
And so that's things like the increase of methane from the permafrost and from wetlands and the collapse of the Amazon and the there's a whole series of carbon feedbacks, but my concern is that the albedo feedbacks, according to Hansen, are a lot bigger than the carbon feedbacks.
Right, and you can change that right here. So again, if right now I'm assuming 0 feedbacks, but if through discussions on such things, we can come up with what is a good number for the albedo. It should be decreased per decade. You can say, well, Hansen thinks it ought to be out here someplace. Well, that's going to affect the temperature this much. So this model allows you to sit down and say, what if the albedo change is this much per decade? And you can put, so I start off at 0, and you can make anything you want to.
Yeah, and so in his latest paper, you included that really good chart from his latest paper, which shows that the cloud feedbacks are 7 times bigger, by his estimate, than the snow and ice feedbacks. Again, that's a really extraordinary. That was quite late in the slide deck. Yeah, that one. That one. So clouds 1.05 watts per square meter. Snow and ice only 0.15, 1/7 of the cloud effect, and the fact that this all adds up to 1.7. That's like the 1.7 is pretty close to the 2 watts per square meter that all of the emissions since industrial times have caused. But this is only over the last couple of decades. So getting the balance between this albedo information and the carbon information is just a critical problem in the whole scenario analysis.
Right, and that's why I stated somewhere that my analysis is based on the data that the IPCC uses, which is primarily the MAGIC model. And then what I want to be able to do is say, well, I start with a MAGIC model. This is how Hansen thinks the model what needs to be adjusted. Here's what we need to take into account this extra factor, which costs this amount of stuff, and you then just go back to the model and you plug it in. So you know you have my starting point, and what if Hansen is right, and the number should be this. So I want to allow you to put in any number you want to put in, and then we can have discussions about what's the appropriate number.
Great, thanks. I think we're on to Ron. Dennis, where's Dennis gone?
Oh, sorry.
Dennis is still there. Yeah, that's
please, Ron, then Mike, then John.
Yeah, thank you, Dennis.
Sorry, just first, could I just mention that because of our the change to daylight saving, there's a bunch of people who are just joining the meeting now, and who are an hour late, unfortunately.
Yeah,
Okay.
I was on the meeting on my phone before I joined, as Dennis probably, or as you know, Robert, because you let me in. Anyway, thank you very much, Bruce. This is really, you know, a very impressive piece of work you did here, and I know you've been working on it for a while. I have, well, one thing, I mean, I think my major point, and I see that Mike is now going to talk after me, so he may be raise this better than I can. But the what I my major what would be nice would be to have something like this that would do a very different kind of analysis. And I don't know if this is in your bailiwick, and I know that it's very presumptuous of me to even assume that you would want to start all over again with a something a little bit, pretty different. But what we're missing really is the risk analysis. That's what we're missing. I mean, we have forecasts, there's just, every time we open a paper, there's a new forecast, and they're all terrible. I mean, they all show that we're headed over the cliff. I mean, no question. I have one here. I mean, we've got one in a paper. I think it's in our paper anyway, a paper I recently submitted. So we need to cut 43% by 2030. That's, in 5 years, we need to get down to 44 gigaton. This is CO2 equivalent, not just carbon. And right now we're, I think, somewhere I have the number here somewhere, but it's just we're going up instead of going down, and the chances of us getting down to 44, just to have a 67% chance of staying below 2 and get to 0 by 2070. And then after 2070, we have to, get rid of, as you, I'm sure you well know, millions of tons, million, I don't know, somewhere in that order of magnitude of GHG equivalent, just to get the temperature down. So I mean, I think the issue is that I think it's very clear to anybody that looks at any of this stuff that there's just no hope doing it strictly with greenhouse gas emissions in the near future. And if we don't do that, then we're, all kinds of terrible, calamitous things are at very high risk of happening. And the risk seems to get greater and greater and sooner. So for many of those things. So I think the real thing, so for one way you might be able to, I mean, at least like to have a very large, to just model this scenario I just said and have how much negative emissions would you need? I noticed in your graphs, you don't have a lot of, doesn't go down to negative often in the ones that you showed anyway. Maybe they're partial representations of what you have in there, but it would be interesting, just how crazy all this thinking that somehow through emissions reduction and even emissions carbon removal, we're going to be able to avoid going up to, the latest UN thing is like 2.7 to 3.1, at least by 2100, which would be a disaster. So I think what would be really useful would be how just a risk-based model, like what kind of risk are we actually accepting right now? And how do they compare with the kind of risks that we don't accept for airplanes, for buildings, for bridges, for anything else? But we're accepting this risk for, basically the collapse of human civilization, likely if we allow this to continue. So I mean, I know I'm just sort of repeating what many of us already know, but this is I wonder if there's some way to just rework this, because we have thousands of people working on these kind of forecasts and stuff, and then this other thing would be more helpful. Thank you.
Bruce, do you have a comment?
Yeah, if you could figure out a formula or an equation or a simple model, I'm glad to work with you on it. The question is, how do you articulate what the risk is? Define the risk.
Mm-hmm. Mm-hmm.
Well. Yeah, no, I get your point. But that is I think we could put in we have their estimates. I mean, everything is the part of the problem is it's the unknown risk, right? It's the unknown It's not so much the known probabilities as what we anyway. But
I think we got
I mean,
the
I get it, but
I do a little
go ahead.
bit here. It's
Yeah.
somewhat here. I have a cost, and the risks are here. Disaster costs going up. If you go back to your a moderate scenario and you come down to cost, you can say if I keep in my moderate scenario, my disaster costs are going to be this. The cost of sea level rise is going to be doing this. If you put carbon removal in, it's going to be this. I don't have GDP change. This is how you risk is more. What is risk? Risk is dollars and cents primarily. And where do those dollars and cents come from? Well, if we can articulate what causes those dollars and cents, I can add them up.
Yeah.
I can say,
sorry, I'm an economist by training, so the dollars and cents is a little bit problematic because, of course, the U.S. The higher costs are in the developing countries where you have all this expensive infrastructure and so forth. So it doesn't really, it is a biased measure. The real thing that I think is kind of human suffering and other species suffering. So that would probably be a better measure. Red, yellow, green.
Anyway, let's move on.
No, but I mean, part of that's part of the issue.
Please, let's give other people
structural models are a little bit. Anyway, thank you. Yeah, I'll shut up.
Very good. Okay, great. Let's move on to Mike. I'm sure he has some very interesting observations. Mike?
Well, I'll come back to Ron's point in a moment, but my simple question at the start was, given that you want people to be able to use this, does it really make sense to show resolution every 5 years, or can you spread that out to 10 or 15 or 20 years or something like that? You might do the calculations every 5 years, but I guess for people interfacing the thing, it would seem to me that you would try and have considerably simpler tables than some of this kind of thing.
Yeah, that's easy to do. I can calculate. I can show it. I can show any range you want. We just have to figure out. That's if we get a group together to work through changes, I can have a button which says how do you want it? How do you want the resolution? Do you want it in 5 year, 10 year, 20 year, whatever you want?
Yeah, I mean, I think it's doable. I'm just sort of so back to Ron's point about can you show risks? So, I mean, there are people who have done this. Of course, Ron in economics, Bill Nordhaus won the Nobel Prize in economics for sort of putting something together, and it was basically a parabola impact, a parabola curve or something like that. They've gotten maybe a little bit better, but there are things that are like. There are two terms. They unfortunately have the same set of initials. There is the social cost of carbon, which is which is a number where you try and estimate the impacts bottom up, and you try and estimate what the cost equivalent is for each ton of emissions, and you get a social cost of carbon, and that's been proposed to use in some of the planning and everything, and there's ranges of values, but there's a whole literature on the social cost of carbon. So $100 a ton or 200 or whatever you want to take. I'm not quite sure how you would use that in some of these things, but I guess you could back it out from you may be able to back it out from whatever the forcing is based on a CO2e or something. The other one, which might be actually more interesting, is the shadow cost of carbon. And that's the cost that it takes to meet some particular standard. So if you said, this is based on sort of how much would it cost to do the energy of it. So if you wanted to say, I don't want to go over 2 degrees, and I know whatever the emissions are for that, how much do I have to pay to change the energy system to make that happen? How much do I have to invest in the energy system to make that happen?
Right.
And if you chose a temperature that was I guess when the Paris Accord was set and they chose 2 degrees, that was a political decision, but it was a political decision saying essentially that we say the risk of going over 2 degrees is such that we don't want as a society to do it. And then the island nations argued that that's too high a number. It should be 1.5. They really probably should have said 1 if they're interested in sea level rise, but whatever. And then you would figure out, well, what is the cost to actually make that happen by transforming, all the different industries and cars and everything else, and that number goes high. But there is a literature on costs, and it might be able to, might be possible to try and figure out as you go. If you took a equivalent of Nordhaus's parabola, sort of relationship that as the temperature goes up, the thing is going up by the sort of square of the temperature difference, that you might be able to figure out a difference between different levels of what a cost is.
I would recommend Steve Keen on that actually, rather than Nordhaus, but yeah.
Well, no, somebody, I don't, yeah, right.
Yeah, what's missing?
Nordhaus got a Nobel. I'm surprised, but yeah, okay.
Yeah, what's missing here in the cost curve is a cost of mitigation. It costs something to do even on a normal scenario, but it's going to cost for mitigation. I don't include all the costs associated with the Earth system stuff. And it'd be interesting to get the mitigation costs in here also, so you can see how much is not only do I want to, if I want to bring CO2 emissions down faster, it's going to cost a ton of money, and I don't have that. We could add that in somehow. If
the other way to do it, and I know this fellow Dave Tattersall has sort of done it, is basically saying that for every ton of carbon that you're emitting above, to take you above some level, the cost of removing that carbon by, say, direct air capture, because that's the only way that sort of has infinite capacity potentially, I guess, is, a couple $100 per ton. And so every time you get going up there, that's sort of a unfunded mandate is what he sort of calls it. There's nobody who's supposed to, who's going to step forward and actually pay for that, though the emitting countries presumably should somehow. But that gives you a cost of, if we really say 1 or 1.5 or whatever is where we want to be, the cost is removing the CO2 that would get you back down to that level. Now, Oswald, I don't know if he's on here or something, he would say, well, if it's methane, if we can reduce methane, that helps reduce the forcing, and there's lower cost by doing it that way. So you could, if you think that will work, you can say that that's a way of trying to pull the forcing down, but you could probably get a cost of pulling the forcing down back to some level that you want it to be.
Yeah, Prince, I didn't show, but if you wanted to go in and say, here's the model, here are the methane emissions. That's what I've got. If you could go in here, you could change these values for methane a couple of ways. I have what's called an aggressiveness ability. So I could go and say I want methane to be much more aggressively done, and I could bring that methane. What did I get? That was CH4. Did that work right? No, it didn't work right. That should change anyway. I can look at how I change how much. Because that's because these are our set values. If I go in, because I put these in, if I go into a, it takes along that way.
Bruce, we're not seeing your page.
I'm not sharing. Okay, I'm not sharing. Okay, there are ways in which the model can be used to say how much do you want to reduce methane. Yeah, this is the sort of thing where when we get a committee together, we can say what are the sort of things which need to be in this. What capabilities do I need?
Yep. And I'd like to get
the other trouble, Ron, with doing a risk analysis, or the challenge of doing a risk analysis, is they don't focus on using the central value of what a change would be in doing a risk analysis. You tend to use the sort of upper bound or something so that you protect against the worst plausible outcome. Is what you want to do in a risk analysis. This is all best based on the sort of central estimate of things, I think, not sort of the range of what it could be. I'm sorry, I'll stop.
Very good. Very good. Thanks, Mike. Let's move on to John and then Robert. And I'd like to leave a little time to go back to that slide about how can we help? What's the next steps so that we don't miss that opportunity here? John?
Thanks, Dennis. Bruce, there's an impressive amount of work in what you've shown us today. It's just, I imagine the many, many hours and days and nights that went to it. Now, my questions were basically building off or, picked up by Ron and then by Mike. And the first one was the general space of risk analysis and whether, that's, you didn't set out to create a risk analysis, but I'm wondering whether there's any ways to adapt the model to work with some of the tails, which was just Mike's closing point. Could you work with the upper, one of the issues is the long tails in this work. So is there any way that you could, without doing a huge lot more work, enable the model to work with the tails or to show the user as a result what's the implication of focusing on the tail, not the median or average value? So that's just one thought. Or related to that, is there any way to give a user a perspective on the degree of confidence in the output? And I know, now I'm talking here about internal rather than external data variability. That having built the model, you realize that some of the underlying equations had higher likelihoods or R-squareds, or they were better fits and others were less good. So you've already got an indication of the internal, or you could perhaps draw out the internal variability or confidence in the model, as opposed to the confidence around the external data, which is either fixed or plugged in. So that's just one thought. The other thought I have was and I really, think the discussion around costs is very important, both mitigation or input costs and the impact costs. My thought was that, number one, costs for emissions reduction or CDR or SRM are going to reduce over time anyway. And that's just what happens with technology. So I didn't hear you speak to that question, although you must have thought about it quite a bit, that reduction in cost over the decades of any particular method. Second, I suppose that you've just made some assumptions about which particular technique was used for SRM or for CDR. And I didn't pick up, obviously, the phasing of the use of the different techniques over time. Now, I'm sure you've got it there somewhere, but I did, and it must be built into the scenarios, but I didn't pick it up.
The screen shows what I do. Can you see that now, the cost curves?
Right.
Yeah. So when I put on carbon dioxide removal, dollars per ton, and starting in 2025, I say I don't know what the costs are going to be. So what I've got is, again, I want my model to be to think anything. So I've got here the costs I'm using right now, $100 a ton, now going down to $30 a ton in 2100.
Okay, it's pluggable, right?
It's pluggable, and I can add more to this. So the whole idea on the cost is, I don't want to have the model say this is the cost, this is whatever. I want the user to be able to say, oh, what if it's this?
Yeah.
That's excellent, righto. That gives us the flexibility as a user.
Yep.
And the curves over time, those are the options of the diminishing cost. Great, very good.
Easy to add more.
Okay.
Again, this is what I call the swag, the scientific wild ass guess. This is what these things were.
I like it.
All right. Well, I suggest we have Robert as our last commentator, and then we go back to the slide of where do we go from here and what help we can provide. Robert?
Yeah, thanks. I just want to compliment you, Bruce, because I know how much work you would have put into this. It's a vast amount of effort has gone in. So well done to you. That's just
Thank you.
superb. The issues for me about this are kind of a top level issues. I mean, I'm not going to get involved in sort of the nitty gritty of the model and the detail, but I think what I'm not entirely clear about is who you anticipate being the user, or what type of people you think will be the users of this model, and what questions are they going to be asking that the model will provide them with answers to that they can't get somewhere else already, because there's a lot of stuff out there. I mean, you yourself have used En-ROADS, so are the people that are going to be using your model the same people that will be using En-ROADS, or are they going to be different people, same questions or different questions, and so on? Because I think that as you move forward with this model and refine it, it needs to be, I think, more focused on the precise value it is going to provide to whoever you perceive to be the user community.
Yeah, good question. When part of initial was the people want to know for a scenario how much SRM is required, how much CDR is required. So it checks that box. It's not at all like En-ROADS, and that it's not a scenario based. This is simply pathway based. You give me a pathway, I can tell you the temperature. So it's in some respects a lot simpler.
The reason I ask the question is because for me there are some very fundamental questions that ordinary people, including ourselves, need to ask, and some of them have been addressed in this session now. And I fear that this model, frankly, is too complicated. You're too much into the weeds, and the sort of people that are interested in these questions are going to look at it and they're going to get frightened off because it's actually very formidable. I mean, what you built is quite extraordinary. I mean, it is superb, but but because there's so much detail in it, it's a bit daunting. And I think the fear that I've got is that you're going to lose some of its potential contribution because of the model's complexity. There's so much going on. There are so many levers to pull. There are so many graphs. There are so many tables. There are so many questions that the user has to ask. And that to me is, it's something that needs to be worked through, because there are some people that will want to go into that level of detail. But my suspicion is that there are a lot of people that won't, and they need to be served as well.
Right. But again, let's come up with a list of what those questions are and how you want to present it. I'll add another menu option which says, oh, you only want to know the top 10 things, click here. And you can explore some other options, the best thing. Let's talk about what those would be and what information we want to provide to those people, and I can display it.
Very good. Very good.
One last comment. One last comment, and I would like to. I would be much happier if the entire model said absolutely nothing about costs, nothing about economics, nothing about dollars, nothing about money, because I think that by bringing the cost issues into this discourse, it completely undermines all of the environmental arguments, because ultimately you're saying that you're giving policymakers the opportunity to say, I know we should do this, but we're not going to save ourselves, but we're not going to because it's too expensive. Well, ultimately, the cost is irrelevant. The cost is irrelevant. It's the last thing.
I disagree. It's right now, the assumption is that we'll pay for it and costs aren't an issue. Therefore, we don't do anything because we're going to pass the costs on. We'll pay for it when the time comes up. The issue for me is we need to recognize now that we are not going to pay the costs in the future. So if we don't do climate intervention right now, we're dead. And the only hope we have is realizing the costs are high, and therefore we have to do something. But again, we can debate that.
Let's continue the debate on that. Brian, you have a quick one before we go on?
Yeah, the costs are growing exponentially. So part of what Bruce is right, and it's an existential threat to our civilization. So what cost would we not be willing to pay? But then finally, when it comes to outreach, I think we have an executive summary at the front, a dozen frequently asked questions or 100 frequently asked questions at the bottom, and let people navigate as they will with these kind of executive summaries and FAQs that can help people's questions get answered. Thanks.
Yeah.
great. Well, Bruce, I would like to ask you if you put up the last slide that you showed us, which was the how can you help? There we go. It's up on the screen. And that just could provide a foundation for thinking for a few minutes about the next steps. And it is very, very clear that you have done an incredible amount of work, study, analysis to get us to where this model is currently. And there are so many ways that we could take it forward. For example, alternative models for the general public, the average six-pack Joe versus a scientist, I think Robert was alluding to that. So we have a number of forks in the road to look at. We have a number of bells and whistles that have been suggested by Ron, Mike, and others. And so maybe what I'm drawing from what you said was you would welcome having a working group to actually, have a dialogue, because, you've been working there on your computer more or less alone, with a little interaction with a few people bilaterally. I would very welcome that idea. And it's our tradition in HPAC to set up a working group when we have a particular problem. Therefore, maybe we could formalize this today and say, look, who would be interested amongst those online? We have 20 people online, according to my figures here, who would be interested to participate in a working group, which could meet on a regular basis to work on the ways in which this model can be improved for utility. And so would that be your view of how to proceed, Bruce?
Yes, ideally. It's been a Lone Ranger so far. These are my ideas, my thoughts, and I'd love to get any early input as to and expert opinions to figure that out. And again, what I'm hoping is this is a foundation, which we then we find all these. We keep talking, but we never do anything. We never bring anything together. This may be a chance to do that.
Yes, exactly. That's what's so exciting about it. So let's go from being a Lone Ranger to being the posse. Huh?
Yeah, there you go.
And we'll get out there on the range. I wonder if just have a round of hands raised of who would be interested to participate with Bruce in a working group that could meet on a regular basis to do this. Yeah, maybe hands raised or hand in your screen, and maybe Bruce, you could write down the names as we go. Yeah.
How about just emailing to me? I'm terrible at the names and email addresses.
Oh yeah. Okay.
Email you or email them to me, or it's email them to the group.
Yep. Okay.
Simpler.
There are some that have raised their hands, so I'm going to write their names down, and then we can specifically communicate with them as we go forward. And I was hoping, Mike, you might raise your hand.
I've got so many things going. I've got to do the other stuff. I can't.
Okay.
I mean,
well,
I'll keep
that's
an
the
eye on
general
it.
problem here.
I'll keep an eye on it, but
We'll draw on you as an intermittent consultant, Mike.
Where Mike can be most useful is other people we could talk to say, I need this information. Where do I go?
Yes, exactly. Excellent. Well, I guess the other thing is we can also send out an announcement about the first.
We're forming a committee. Yeah, get back here.
And they show up. Yeah, that would be another way to do it. And so let's do that. I will work with you, Bruce, to organize that so that we develop a community around this, and look at the ways we can do that, and then get it up onto the website so that it can.
It is up and running. In fact, I forgot to mention that it's on there. It's very simple. The Scenario Explorer, scen.exp.org. I'll put it in the chat. And if something's running, look at it.
Please put it in the chat, and we can then all have a look at it at our leisure and develop more ideas and reactions to it. Fantastic. Okay, well, that probably would be the best thing we can do rather than go through the whole list of that group can actually deal with that group of questions that you have about how we can help to move this along. It should be a fun thing to do, and lots of ways in which this can be taken forward. I see that Robert, you have your hand up. Did you want to make another comment?
Oh, no,
Robert?
sorry.
Yeah. Okay. All right. Are there any other suggestions about how we take this forward as an HPAC activity? Okay. Well, I think then we have, it's 1.5 hours. We reached the end of our time slot. I think on behalf of all of us, we are blown away by what you have done here, Bruce. Absolutely blown away. And of course, it's a journey. You're the first to recognize that and how we can further develop it and further create the dashboards that could be useful for general public, for scientists, et cetera, to use this for any number of ways in asking and answering questions that they come up with. So again, thank you so much. We just really, really appreciate it. You're an HPAC hero, man. You have come up with something that was so needed, so useful. For those of us who were familiar with En-ROADS or the reflective emulator, we saw those as partial solutions, but they didn't have the comprehensiveness that you have been able to develop. So thanks once again. And on behalf of all of us, we look forward to working with you to make this better and to get it out there so the public can use it, and a source of great debate and discussion as we use the model and formulate our interpretations of what comes out. So,
and I will be presenting this thing in Cape Town I have a poster session in Cape Town, this global conference in May. So we'll get a lot more feedback there, I hope.
Fantastic. And hopefully a few of us will be there to join you and back you up there. Yeah. Okay. Well, thank you all very, very much for joining us. And we'll be in touch with the first meeting of the working group and get started on further improvements on the model.